Maxima and minima. Simply put, local maxima and minima are high points and low points of a function. An absolute maximum on an interval is the highest point on the interval. An absolute minimum is the lowest point on an interval. By definition, local maxima and minima occur at interior points of an interval. A local max can also be an absolute max, and a local min can also be an absolute min. A function that is continuous on a closed interval will have an absolute maximum and an absolute minimum. We have here a function that is continuous on a closed interval, so it will have an absolute max and an absolute min. Let's look at a few points. Here we have a local maximum. And here we have a local minimum and it's an absolute minimum. This is not a local minimum because it is an endpoint. Endpoints are not allowed to be local max or mins. This point is the highest point on the interval, so it's the absolute maximum. But as I said, it can't be a local max because it's on an endpoint. If f has a local minimum or maximum at a point C, then and if you know that f prime of C exists, then f prime of C will be 0. So if you have a local max or min and the derivative exists, then that derivative will be 0. Local minimum or maxima can also occur where the derivative does not exist. And so here's the point. Your local maximums and local minimums will occur either where the derivative is 0 or where the derivative does not exist. And so what we do is we define a critical point to be a point where either the derivative is 0 or where the derivative does not exist. And a critical point just means it's a point of interest. And that's because all local maximums and minimums occur at critical points. But just because you're a critical point doesn't mean you're a local max or min. Those points have to be checked. So we know that if a function is continuous on a closed interval, then it will have an absolute max and an absolute min. And here's the procedure to find the max and min. You locate all your critical points, you evaluate the function at the critical points and at the end points, and then you choose your largest or your highest and your smallest. Lowest would be a better way of putting it. And let's do an example. All right, so we want to find the absolute max and min, so we need to find critical points. In order to find critical points, we have to take the derivative. So take the derivative, and then let's just remind ourselves, a critical point occurs if the derivative equals 0 or the derivative does not exist. Now, this derivative is a polynomial. There's not going to be any place where the derivative doesn't exist. F prime is defined everywhere. So to look for critical points, we're only going to look for where the derivative equals 0. So we just take the derivative function and we set it equal to 0. And so either x squared is 0 or 2x minus 3 is 0. And that gives us two critical points, 0 and 3/2. So we have two critical points, 0 and 3/2. And we're going to evaluate these critical points, and we're also going to evaluate the function at the end points. And I like to make a table. So here I have a table. I've got two critical points I need to check out, and I have two end points that I need to check out. And I just evaluate my function at those points. And one thing I want to emphasize here is you're evaluating the function at these points, not the derivative, the function. And then what we're looking for is your highest and your lowest. And our highest point is at -2. We have a height of 32. And our lowest point is at 3/2. We have a height of -27/16. And so our absolute max is at our highest point at the end point, and our absolute that min is at 3/2. And so you might have recall we had a critical point at 0. Notice that it's not a local min and it's not a local max. We have another function here for you to look at. In order to find the derivative of this function, I would first multiply out that x to the 2/3. I'd go ahead and distribute that and multiply it. That way you don't have to use the product rule. And then you take the derivative and oh my goodness, what an ugly looking derivative that is. Here's my recommendation on how to handle it. Notice how you have a 3 in the denominator and you have x to the negative 1/3 in one of your exponents. So I would multiply this function by 3 times x to the 1/3 over 3 times x to the 1/3. And then when you distribute the 3x to the 1/3 in the numerator, when you distribute that into the parentheses clean up really nicely. Now just a reminder, critical points occur where the derivative equals 0 or where the derivative does not exist. Now this function, this derivative does not exist at 0 because that would give me 0 in the denominator. So g prime does not exist at 0. Also, we have to look for where g prime equals 0. And so the g prime equals 0 when x is equal to 4/5. So we've got two critical points. So we set up our table. We've got two critical points. I wrote 0.8 instead of 4/5. Just wanted to show you I switched over to decimal notation. And two endpoints. And I evaluate all of these points using my function. So what's my function at at each one of these points? Then I find my highest and my lowest. I've got an absolute max, just it occurs at -1. I have 2 points where I reach my lowest, and my lowest point is 0, and I reach it twice. And here's my function. I have an absolute max at -1. The absolute min value occurs in 2 locations. And this critical point is a local max. It's not an absolute, but it is a local. And that takes care of us for this section. Take care, and I'll see you in the next section. Have a great day.